Welcome to the next entry in the PTX NFC series. In this section, we examine the RL78 G23 microcontroller platform, detailing its capabilities and outlining the process of implementing NFC functionality from the ground up. The RL78 G23 series from Renesas are general-purpose 16-bit microcontrollers specifically designed for low-power applications. It delivers highly efficient low-power performance thanks to the snooze mode sequencer and fast wake-up times. On the 4 KB SRAM variants, current consumptions can be as low as a few hundred nanoamperes. The RL78 G23 series offers a wide range of variants starting from 13-pin packages up to 128-pin options with operating speeds up to 32 MHz. Flash memory capacities start at 96 KB and extend up to 786 KB in higher-end models. In addition to their ultra-low power capabilities, the RL78 G23 microcontrollers integrate high-speed on-chip oscillators, helping reduce external component requirements and overall bill of material cost. They also support a rich set of peripherals, including advanced features such as capacitive touch sensing. For this demonstration, we'll be using the PTX105R Quick Connect NFC peripheral equipped with a PMOD connector paired with a fast prototyping board featuring the RL78 G23 microcontroller in its 128-pin variant. To ensure a flexible solution, the user is responsible for implementing the interface between the two system components. This is handled by the platform component in the software architecture, which depends on the MCU application processor and the physical interface used to communicate with the PTX chip. The platform component includes several sub-modules. The interface, which manages the driver for the chosen communication interface, SPI in this case, the GPIO, which handles the driver for interrupt requests and chip select, and the timer, which provides timeout functionality for the IoT reader stack via hardware timer wrapper. To get the reference hardware configuration, we should look into the quick start guide for this board. By scrolling down, we can find the pin configuration for the PMOD1 port. It looks like the connections are centered around pin 140. We will keep this in mind while configuring the components since the PTX module will be connected through this port. So let's dive into the configuration process. We start by opening an instance of the eSport Studio. For compatibility, it is preferred to use the latest version. We start by creating a new workspace and then proceed to create a new executable RL78 project using the CCRL compiler. We will name the project IoT RL78. In the toolchain device and debugger settings, we select the latest version of the CCRL compiler. For the target device, we choose the 128-pin version of the RL78 G23. Finally, for debugging, we will use a COM port connection. Next, we will enable Smart Configurator and choose to generate a bare metal project. This gives us a clean starting point, allowing full control over how we configure and manage the hardware components in our project. Once everything is set, click Finish to generate the project template. Now, let's open the Smart Configurator file. The first thing we're going to do is go to the components and add a new component. What component are we adding? We'll be adding an interrupt controller. We will name it config int. Once that's done, click Finish. Now we have our interrupt resource added. The next step is to select the interrupt that's associated with our device. In this case, we're going to choose and enable int6. Next, we move to the Pins tab. We'll scroll down and locate pin 140 since that's the hardware mapped pin from the PMOD port to the interrupt 6 module. Once we enable this pin, its parameters will be automatically configured. Now, to configure the functionality of this module, we need to import a few source files. The RL78 G23 folder contains the platform-specific configuration files. So, we'll start by copying this folder into our project directory. Next, we will copy the application files into the source folder. This ensures that these files become part of our project and are included during compilation. When we open the PTX platform file, you will notice several referenced header files. These header files will be generated automatically as we continue adding components to this project. You'll also see some macros defined. One of them is the interrupt flag, which is declared as an external variable. To make sure everything is properly linked, we navigate back to the Smart Configurator and click Generate Code for the components we have added. Now let's navigate to the user configuration file for the interrupt. First, we will define the global variable for the interrupt flag. Next, we will set the flag to 0 during initialization and update it to 1 inside the interrupt callback function. And that's it for the interrupt configuration. Next up is the timer module. The component we'll be using is called the interval timer. We will set it to 16-bit mode and it will use the TAU01 resource. That looks good, so we'll go ahead and click Finish. This will add the timer component to our project. For the clock source, we're using the CK01. The clock frequency is set to 2 to the power of 10 and the interval is configured to 1000 milliseconds. And that's our timer module configured. Now let's generate the code. Once it's done, we should see that TAU01 has been added along with corresponding user code section. There are two files we need to open. One is the user configuration file for the timer and other is the PTX platform file. If you look closely, you will see a variable called timeout flag, which is declared as an external variable. When we click on it, it doesn't redirect to the source file, so we will need to define it manually. Let's go ahead and navigate to the timer user configuration file and add the timeout flag variable there. And now it works. Next, we will set the values for different timer events. At initialization, we will set the flag to 0. Then during the interrupt event, it will be set to 1. And that wraps up our timer configuration. The third component we're going to add is ports. We will select a new component of type ports and simply add it by clicking Finish. For this configuration, we will be using port 0 and port 14. Navigating to the details of port 0, we will select pins P00, 02, and 03 as output ports. Then we move on to port 14. Here, we will configure P140 as an input since this is the interrupt pin. Next, we take a look at the platform file to identify the CS pin, also known as the NSS or SS line. By searching for NSS in the file, we can see that P14 pin 1, that is P141, is hard-coded as the NSS line. So we will configure P141 as an output and set its initial state to output 1. And that pretty much wraps up the port configuration. The next component we're adding is the SPI communication module. We will add a CSI module of type SPI and select CSI 30, which is the one connected to the PMOD1 port. We'll configure it for both transmission and reception. The clock mode is set to internal clock, with the operational clock being CK10. The clock frequency is calculated using a factor of 2 to the power of 2. The transfer mode is set to continuous, and the transfer direction is configured as MSB first. For data timing, we will use type 4. We'll leave the baud rate at 153600. With all settings in place, we will go ahead and generate the code. Now let's navigate to the SPI user configuration file. Here, you will notice that a number of macro definitions and function definition placeholders have been automatically generated for us. Next, we will add a few global variables to act as flags for data transfer. We will set and update these flags within the appropriate SPI functions. Additionally, we will define specific actions inside the callback function referring to serial array unit 12 SAU12. And that wraps up what we need to fill in for the SPI communication user configuration. Now that we have completed the component configuration, the next step is to configure the build settings for this project. Depending on the project requirements, we may opt to exclude certain files from the build. For example, we will not be needing the IoT app test API file, so we exclude them from any build configuration. We can do the same for the RF test folder. We will add some macro definitions under the compiler settings menu. We will start with macros related to the SPI interface selection. The specific macros to be added for this project are listed here. Once we have added all the necessary macros, we click Apply to save the changes. Next, we'll add the include paths for various folders that contain header files used in this project. We'll start by adding the comps folder. Then, we'll continue by adding the RL78 G23 folder. We'll keep adding the remaining relevant folders in the same way to ensure all header files are properly linked during compilation. Alright, we have now added all the folders that may contain any header files referenced in the code. This ensures that the compiler can locate all necessary files during the build process. Alright, those were the essential steps to configure a low-power RL78 board in Smart Configurator and add NFC support. Thanks for watching.